Okay, good afternoon, everybody, and welcome to our fourth ML4LM webinar. And today's talk is actually going to bridge the gap again between the physical land modeling and the machine learning, but this time on the hydrology side of the land surface. And probably we'll be exploring the modeling and machine learning and exploring the predictive skill when AI methods are used, and also their quantification of the related uncertainties. And our speaker today, Dr. Dan Liu, is a senior computational earth scientist at Oak Ridge National Laboratory, where her research focuses mainly on integrating diverse data source and modeling framework, trying to address the complex challenges in the land surface modeling and also in the earth system modeling in general. As a PI, Dr. Dan leads multiple departments of energy in US projects spanning from the earth system modeling, coastal flood prediction, and hydropower forecasting. Also geophysical inversion as well. She received several awards, among which the DOE Early Career Award in 2023. And she is a very active contributor to the scientific community, also serving in editorial boards, and currently serves as an editor-in-chief of the Journal of Hydrology. I will give the floor to Dr. Dan now, just to get in mind that this webinar is being recorded and the recording will be available later on the ML4LM web page. And for any question and the discussion at the end, please use the Q&A section at the bottom of the Zoom window. To you, Dr. Dan. Thank you.
Yes. Thank you, Suhan, for the kind invitation and a nice introduction. So hello, everyone. So thank you for attending. I'm going to share my screen. Hello, everyone. Can you please confirm you can see my full screen in the presentation mode? Okay. Yeah, thank you. Okay. Hello. So I'm Dan Liu, a senior computational earth scientist at Oak Ridge National Laboratory. So as Suhail introduced, my research focuses on advancing earth system modeling by integrating diverse data and multiple models, developing the reliable AI machine learning and uncertainty quantification techniques to improve the predictions, and also accelerating the simulations using the high-performance computing. And today, I will introduce several of our work on the land surface modeling using the Trustworthy AI. And each topic will be covered briefly. So if something attracts your interest and you'd like to understand better, so please feel free to ask questions at the end or reach out by the email here. And my purpose here is to spark a discussion, and so we can work together to advance the earth sciences. So currently, there are three major modeling approaches advancing the earth system prediction: the physics-based models, data-driven machine learning models, and the big data-powered AI foundation models. And the physics-based models have become increasingly sophisticated over the years. But this comes with a high computational cost and the growing challenges in the parameter estimation and uncertainty quantification, as also mentioned by Dave in the second webinar. And then to address these issues, we've developed efficient emulators that significantly reduce the runtime and also make the ensemble simulations affordable. We've also applied generative AI to enable a faster site-specific parameter estimation and UQ at a large scale. And the data-driven machine learning models offer a flexible alternative by learning the system dynamics directly from observations. However, they often struggle to generalize across space and time. After all, they are data-driven, right? So they cannot say what's going on in the future. And they also lack the physical interpretability and also the reliability, especially under the changing environmental conditions. And our work tackles these limitations by integrating diverse datasets, designing the interpretable AI frameworks, and applying UQ methods to improve the trustworthiness of the machine learning model predictions. And recently, the AI foundation models present promising new directions like the ChatGPT. And these models are trained on a massive unlabeled dataset and can be adapted to a wide range of assistant applications. And my team are developing such a model to support weather forecasting, climate downscaling, and even accelerating the physics-based land surface model simulations. And in the following, I will briefly walk through examples of our work in each of areas. And in a typical physics-based land surface modeling workflow, as shown in the left, we begin by collecting observational data and developing the process-based models based on our understanding of the system. And these models contain the uncertain parameters that must be calibrated against the observations to improve the simulation accuracy. And once calibrated, the models are used for predictions. And if the predictions are accurate and the uncertainties are small, then the models can be confidently applied to the real-world problems. And if not, then the models are refined by incorporating the additional data or improving the model structure to enhance their predictive skill. And this process involves the inverse modeling to estimate the parameters and also the forward simulation to generate the predictions. And the predictions are usually full of uncertainty from the data quality, model structural assumptions, parameter estimation, and initial and boundary conditions. So therefore, quantifying and addressing these uncertainties is essential to improving the prediction reliability. And the uncertainty quantification, as you know, typically requires ensemble simulations. And some steps, like the iterative parameter calibration, are difficult to parallelize by leveraging the high-performance computing. And this makes the process computationally expensive. And then to address this, we use the two methods, emulation and generative AI. Emulation involves building the faster surrogate models that reduce the runtime of the individual land surface simulations, enabling more efficient UQ. And however, the traditional UQ methods, like Markov-Chain Monte Carlo sampling, must be rerun each time when the observational data change. And then due to the spatial heterogeneity of the land surface processes, the parameter calibration is often site-specific and requiring the local observations for the model calibration. And then to support a larger scale site-specific model calibration with a high efficiency, we use the generative AI techniques. And in the following, I will briefly introduce these two approaches. And the first approach is emulation. We use the neural network to build the fast emulators of the land surface models trained on ensemble of simulation outputs. And however, as the neural network becomes more complex, as you can see when we use a fully connected neural network as an illustration here, the required amount of training data also increases, and which raises the computational cost of generating the training data. And then to address this, we apply the dimension reduction techniques to simplify the network structure. And this is especially effective for the large-scale land surface models when we are dealing with many the spatial temporal varying output variables. And for example, as shown in this study, training the emulator in a reduced dimension space allows us to achieve the accurate predictions with just 20 simulation samples, while the full dimension models would require around 200 samples for the comparable accuracy. And then once trained, the emulator can replace its original expensive land surface model in the calibration process to improve the computational efficiency during the uncertainty quantification. And however, the traditional UQ methods like the Markov-Chain Monte Carlo sampling remain computationally intensive even with a faster emulator. A key limitation is that the entire calibration process must be repeated whenever the observational data change because the electrical function changes. And then to overcome this, we developed the diffusion-based uncertainty quantification methods using the generative AI. And this DBUQ method is designed to efficiently generate samples from the parameter potential distributions for the model calibration and uncertainty estimation. It first formulates a generative model F capable of drawing the samples from the target posterior. And the neural network is then trained to approximate the F by laying the mapping between the standard Gaussian latent variable Z, the observational data Y, and the potential distribution of the parameters X conditional on Y. And once trained, the network can rapidly generate parameter potential samples by evaluating the standard Gaussian inputs and making this process highly efficient. And it's also memory efficient, so as only the trained network needs to be stored rather than the large ensemble of the parameter samples. And I want to mention that a key advantage of this method is that it enables amortized Bayesian inference. So for any new observation Y, the network can quickly generate the potential samples without the need for retraining. That's because we already learned that the generators using the neural network. Actually, this method involves a substantial mathematical development. So without going into that details, okay, I can show you some examples here, how to apply these methods in practice. And in this study, we estimated the 8 land surface model parameters using 5 years of annual average latent heat flux at the Missouri Ozark magnetic flux site. So we conducted 2 case studies. In the synthetic case, we randomly selected 1 simulation sample as synthetic choose and synthetic observation. And in the real data case, we used the actual site measurements. And then to evaluate performance, we compare the potential distribution estimated by our DBUQ method against the loads obtained from the traditional Markov chain Monte Carlo sampling. And for a fair comparison between these 2 methods, we use the same 1,000 land surface model simulation samples. And in the MCMC simulation, we use these samples to build the emulator and then evaluate the emulator in the MCMC process. And it took about 5 hours to generate the potential parameter samples after the emulation. And in contrast, the entire DBUQ pipeline completed in less than 10 minutes and achieving a 30 times speed up. And now let's look at some results here. So we performed 2 synthetic case studies to evaluate generalization capabilities of the DBUQ methods. And in both cases, DBUQ accurately estimated the parameter potential distributions with the PDFs closely matched those obtained from the MCMC. And it also consistently estimates the true parameter values with a high probability. And furthermore, these prediction samples derived from the parameter potential samples closely match the synthetic observations and demonstrated a tight spread as illustrated in this box plot. And these results indicate that DBUQ can effectively calibrate land surface models. And in the real data case, where we calibrated the model using the actual site measurements, DBUQ again demonstrated a high accuracy in both the parameter uncertainty quantification and the model calibration. And the results from the DBUQ closely match those from the MCMC, showing the similar potential distributions and the predictive performance. However, DBUQ achieves this with only a fraction of the computational cost, achieving a 30 times speed up when calibrating the method with just a single observational set. And this efficiency becomes even more important when scaling to the multiple sites for the larger scale set-specific parameter estimation. And our method has been applied to a wide range of scientific applications. And if you are interested, please go to this GitHub for more details, and which includes the source code and the related publications. And so far, we talked about the challenges in the physics-based land surface modeling and introduced the 2 approaches, emulation and the generative AI for the efficient model calibration and UQ. With the advancements in the satellite remote sensing and the in-situ sensor networks, researchers are increasingly using the data-driven machine learning models to simulate the terrestrial ecosystem dynamics. And these models leverage the extensive and diverse data sets opening new possibilities for our land surface modeling. And the machine learning models, such as long short-term memory networks, are widely used to capture relationships between the environmental drivers and the responses, laying the system behaviors directly from the data. And while these models have shown great success in the prediction, they also raise critical questions about the trustworthiness. So for example, how can we ensure that the machine learning solution generalizes across different spatial and temporal scales? And how do we verify that the models are making good predictions for the right reasons? And more importantly, how can we guarantee the reliability of the predictions under the changing environmental conditions? And our approach tackles these challenges by focusing on the three interconnected areas. So first, we integrate diverse datasets with advanced model architectures to enhance the prediction accuracy and also improve the generalizability across the different spatial and temporal scales. And additionally, we incorporate explainable AI techniques to validate the model decisions, ensure the physical consistency, and also identify the key drivers to the predictions of the response variables. And this not only will deepen our understanding, but will also guide the target data collections from this explainable AI. And furthermore, we also quantify the prediction uncertainty to evaluate and ensure the reliability of the machine learning model predictions, especially under the changing environmental conditions. And in the following sections, I will go through each of these areas in detail. And first, let's dive into the first area, how integrating the diverse data with advanced machine learning models improve the prediction accuracy and generalizability. As we know, accurate long-term stream flow forecasting is crucial for the effective water resources management. And however, predicting the stream flow over the extended time horizons remains a major challenge. And then to address this, we developed a temporal sequence transformer, TST, which is a machine learning model that integrates the past weather observations, future weather forecast, and historical stream flow data to improve the 1 month ahead stream flow predictions. And this TST model architecture, as shown in the right figure, includes 2 encoders to process the historical and future driver data, and 1 decoder to process the past stream flow information. And across temporal fusion module helps denoise and integrate the encoder outputs, while the decoder uses a cross-attention mechanism to combine this encoded information with the past stream flow for the future predictions. We applied these methods to forecast the stream flow 30 days ahead at about 200 catchments across the United States. And the results indicated that, as shown in the left figure, so our TST model achieved a high prediction accuracy across all catchments and even at a lead time of up to 30 days. And then taking a closer look at these results, our TST model outperformed the standard long short-term memory networks, the encoder-decoder LSTM networks, and the physics-based VIG hydrological model. And the TST achieved higher prediction skill scores and maintained robust performance, even when driven by the noisy weather forecast input. And this study underscores the potential of the advanced machine learning models, like the TST here, to enhance both the prediction accuracy and also the temporal generalizability into the 30 days ahead, and by effectively integrating these multiple data sources. Okay, in the previous study, we trained a machine learning model to predict the stream flow for specific basins using the historical data. However, most basins are ungauged, lacking the historical records, and which presents a significant prediction challenge. And then to address this, we developed a regional machine learning model trained on the data from the gauged basins to predict the stream flow in ungauged basins. And then to improve the model training, we incorporated catchment attributes such as soil properties, geology, and the topography. And for basins, without the catchment attribute data, we developed a machine learning approach to extract the relevant land surface information from the widely available remote sensing data. And additionally, we can combine all these available input data, such as meteorological forcing, catchment attributes, and remote sensing information to maximize the model performance. And we applied all these 4 machine learning models to predict the stream flow across the corners and demonstrating their capabilities to address the challenges of the ungauged basins. And in this study, we used the Camon's dataset for the model training and the validation, employed a 3-fold cross-validation to assess the spatial and temporal out-of-sample prediction performance. The results indicate that the machine learning models integrating the diverse data from the gauged basins and the satellite image and outperformed other approaches in predicting the stream flow at ungauged basins under future meteorological conditions. And this study highlights the potential of advanced machine learning models that combine the gauged basin data with the widely available remote sensing data to significantly improve the prediction accuracy and also enhance both the spatial and the temporal generalizability. And beyond achieving the accurate predictions, we also aim to understand why the machine learning model performs well and what are the key drivers contributing to its success. And in one project, we used the encoder-decoder long short-term memory networks to forecast the reservoir inflow a week and a month ahead. And to analyze the hydrometeorological drivers behind this forecast, we applied the explainable AI techniques. We started with the off-the-shelf sharp methods to evaluate the inflow predictions across the multiple reservoirs in the western and southeastern United States. And the results aligned with our physical understanding. So, for example, in the snowmelt dominant basins in the western US, temperature was a key driver of the inflow forecast. And in the rain-driven basin in the southeastern United States, precipitation played a dominant role. And across both regions, historical inflow consistently emerging as the most influential variables. And these insights reinforce the confidence in our model's decision-making process. So it helps understand that machine learning model not just memorize data, it actually learns some consistent important drivers. So to confirm the machine learning model's predictions decision-making. And however, the sharp methods had some limitations. It was computationally expensive. The computational complexity is about 2 power n, and where n is a number of features. And it couldn't separate the individual and the interactive contributions of the drivers. And then to address these limitations, we developed a more efficient integrated gradient methods. So this IG approach not only accelerated analysis, but also provided deeper insights into the individual drivers' impacts and their interactions impact. And we applied this integrated gradient method for the 30-day inflow forecast across multiple reservoirs in the Upper Colorado River Basin and gained a good understanding of the machine learning-driven predictions. So as we know, the terrestrial ecosystems are inherently dynamic, while the drivers usually have the memory effects on the response predictions over time. And then to better capture this complexity, we go beyond just assessing the variable importance to also investigate their temporal importance in the system predictions. Then to achieve this, we applied a range of interpretable machine learning approaches. So as shown in the left column, in these attention-based transformer models, so the self-attention mechanisms identify the temporal patterns within each driver itself. And while the cross-attention mechanisms capture the relationships between these drivers. And then by extracting and visualizing these attention values, we can validate the model's learning process and also ensure it aligns with our understanding of persistent relationships and the dynamics. And in another study, as shown in the right column, we developed an interpretable long short-term memory network to predict water and carbon fluxes using multiple environmental drivers while simultaneously analyzing both the variable and the temporal importance. And different from the standard LSTM models, which mix the driver's dynamics within the hidden states using a vector. And our interpretable LSTM uses a variable-wise heat matrix. So this design captures the distinct influence of each driver, enabling a more detailed evaluation of how different variables interact over time and how they can combine influence our response prediction. And when applied to the carbon flux prediction, we demonstrate that this interpretable LSTM not only achieved higher accuracy, but also revealed the new relationships between the environmental drivers and their memory effects on the carbon flux prediction. And these insights can actually inform the process-based land surface model development and also improve our understanding of the terrestrial ecosystems. So now we introduce the several explainable AI methods. So the explainable machine learning techniques help us understand why a model performs well, but it's also important to understand when and why the model may fail, especially when simulating a dynamic terrestrial ecosystem under the changing environmental conditions. We know that the data-driven machine learning models often struggle to maintain a good performance, especially under the new or unseen conditions. After all, they are data-driven. They only see what's happened in the historically, and they don't know what may change in the future. So, and as shown in this example, so a LSTM model trained on the 20 years of data from a relatively cool climate struggle to predict the stream flow during the subsequent warmer years. And as you can see, the performance quickly dropped in the when they evaluated in the relatively warmer years. And this performance drop highlights a key limitation, that is the machine learning models can fail when applied to the evolving climate scenarios. And then to ensure the reliable prediction, uncertainty quantification plays a critical role here. The UQ can help detect situations where the model is likely to make poor predictions by flagging the high uncertainty as a warming signal. And then despite the importance, uncertainty quantification for machine learning models remains challenging. Current state-of-art methods come with trade-offs. So as I listed the 3 state-of-art methods here. One is the Bayesian neural networks. It provides rigorous uncertainty estimates, but are also computationally expensive. And Monte Carlo dropout and the deep ensemble methods are more practical, but they rely on the strong assumptions, like the Gaussian assumption here, that may not always hold in practice. And the most prediction interval approaches introduce additional hyperparameters, often leading to the unstable training and unreliable performance. And these challenges highlight the need for more efficient and robust UQ techniques that can balance the accuracy, computational cost, and the stability. And then to address these challenges, we developed a novel prediction interval method called PS3NN to quantify the machine learning model uncertainty. So the procedure is like this. For a given confidence level, this approach estimates the prediction interval using 3 neural networks in 4 steps. So first, we train a neural network to estimate the prediction value, no matter what neural network it is. So like you usually do, depends on the data type, you pick the suitable neural network to make a deterministic prediction. And then based on the prediction errors, we train 2 additional neural networks to estimate the up and the lower bounds of the interval. And lastly, we calculate the 2 coefficients to precisely determine the prediction bound, the uncertainty bound for a given confidence level. And we have applied this PS3NN to multiple scientific problems and already demonstrated it can produce the accurate and reliable uncertainty estimates that precisely enclose the specified portion of the data with a narrow interval width. So for example, if you give it 90% of confidence level, it will guarantee it will enclose about 90% of your data with a relatively narrow interval width. So let's look at the example. In this study, we applied the PS3NN to quantify the uncertainty in the LSTM stream flow prediction for 2 catchments in the East River watershed. And at the calculate the catchment, where the hydrometeorological conditions in the test period were similar to the training period, PS3NN accurately quantified the uncertainty, aligning well with the confidence level. And at the Log Creek catchment on the right, so where the test condition different from the training conditions, the machine learning model struggled due to the data shift. But the PS3NN can detect this data shift by producing a wider uncertainty range and consistent with the larger prediction errors. And this error-consistent UQ approach is particularly valuable when machine learning models are used to predict the future conditions or the regions without the ground truth data available. And then by acting as an error indicator, this uncertainty estimate helps prevent the overconfidence in the predictions and also ensure their reliability under the changing environmental conditions. And additionally, this quantified uncertainty can guide the data collection. We can observe where the uncertainty is large and then purposely to get more data to reduce uncertainty and also help us to further improve the model and to reduce that uncertainty. So this uncertainty quantification actually serves as an error indicator to help us to avoid overconfidence and also guide us for the future data collection and the model development. And then so far, we discussed both process-based models and the data-driven machine learning models. And both modeling strategies require the observational or the labeled data, either for the calibrating the physical models or for training the machine learning models in a supervised learning framework. And however, Earth system data are largely unlabeled and multimodal. As shown here, we have the time series and we have the image data from the satellite, and we also have a large number of database. And then how to leverage this massive heterogeneous data to improve our modeling and understanding of the system. And then here the foundation model comes into play. A foundation model is a large-scale neural network trained on the vast, diverse dataset in a self-supervised manner, and it then can be fine-tuned for a wide range of modeling tasks. These models operate in two phases, pre-training and fine-tuning, and relies on 4 pillars: data, model, compute, and applications. And during the pre-training, the model learns the general representation of the Earth system by processing the large heterogeneous dataset, and is then fine-tuned using very limited observational or simulation data as labeled data to adapt to a specific tasks. And these models are usually large and often with millions or even billions of parameters, allowing them to effectively process the massive datasets. And their performance generally scales with the data and the model size. And while the pre-training is computationally intensive and requires the supercomputing resources, and the fine-tuning is relatively fast, making it practical for the real-world applications. And once trained, the foundation model can be leveraged for a variety of tasks, including the short-term weather forecasting, the long-term climate prediction, the climate downscaling, and even accelerating our physics-based numerical models. And as you can see, these capabilities make these foundation models particularly well suited for our Earth system modeling. So the Earth system generates vast and diverse datasets from the in situ measurements, remote sensing, temporal database, and then numerical simulations. And these datasets have multiple types and different scales and different resolutions, and making the full integration very challenging for the traditional numerical models and for some task-specific machine learning models. And also, much of this data remain unlabeled and limited its utility for the task-specific, especially the supervised machine learning models. And then recent advances in the vision transformer architecture allows us to integrate this heterogeneous dataset, and this transformers model's performance has been demonstrated improving as the data volume and data resolution increase. And more importantly, the Earth system simulations have broad scientific applications and impact multiple sectors, and making this foundation model a powerful tool for advancing research and also informed decision making. And then by leveraging this foundation, we can fine-tune it to enhance the modeling tasks while reducing the computational cost and the individual efforts and the energy consumption. So think about this. So each individual right now build their own task-specific machine learning models to address their specific scientific problems. But right now, if we have this foundation model is pre-trained and delivered to you, and then you can leverage this foundation, just fine-tune it a little bit with a limited labeled data, and then can address your own specific problems. So eventually, it reduced overall the computational cost, the human efforts, and also the energy consumption. And then we are currently developing a foundation model for the Earth system modeling called the Orbit. And the Orbit is pre-trained on the CMIP6 climate simulation data. And we leverage the ESGF for the data access and the PMP package to select the high quality data set for training. And currently it incorporates 91 variables, including the temperature, wind speed, humidity, geopotential, spanning the surface up to the 17 atmospheric layers. And to explore how model performance scales with the data size and the computational cost, we have designed a full version of the Orbit, ranging from the 100 million to the 100 billion parameters. And this evaluation can help us optimize the scalability based on the available data, based on the available computing resources, and also the accuracy requirements. And because of this 100 billion parameters model, it also makes our Orbit the largest AI models for the Earth system modeling to date. And our evaluation indicates that the larger models are more effective at processing the vast data set and capturing the complex patterns. And then also given the petabytes of the simulation data available from the CMIP6, so CMIP7 will be online with the petabytes of the simulation data. So Orbit can leverage this large volume unlabeled data during the pre-training phase, and then reduce the requirement of the labeled data in the following the task-specific fine-tuning case, while also accelerating the simulations for your task-specific problems. Then to accelerating the training of this large-scale model, we implemented the hybrid parallelisms, combine the model tensor, model pipeline, data, and the sequence parallel techniques in an orthogonal design, and then optimize its scalability on the ORNL's frontier supercomputer. And the Orbit has demonstrated a strong scaling efficiency of up to the 85% across more than 6,000 frontier nodes, and ensuring the efficient use of computational resources. And this exceptional scalability enables Orbit to rapidly generate large ensemble simulations, which are critical for the uncertainty quantification and capturing the low probability extreme events at their tails. So in the following, I will show you 3 fine-tuning tasks by leveraging this Orbit foundation model. So in one test, we fine-tuned the Orbit with the ERA file reanalysis data for the weather forecasting, and demonstrated comparative performance against the state-of-the-art numerical models, machine learning models, and the foundation models. And then after training, Orbit can produce the forecast in less than a second, just on a single GPU, and making it possible to run the weather forecast on your own laptop and rapidly generate large ensembles for the probabilistic prediction. And besides the weather forecasting, we are currently fine-tuning the Orbit for the weather and climate downscaling, so a critical process that transforms the coarse-resolution weather forecast and climate model projection data into the high-resolution data needed for the regional impact assessments. And this final scale information is very essential for the multiple sectors, so including the water resources management, infrastructure planning, and also the disaster risk mitigation. But we know that, so in the previously, I show you the we fine-tuned the Orbit for the weather forecasting. That's the temporal prediction problem. But here we are doing the downscaling, which is image super resolution problems. For these totally different problems, we can leverage both this foundation model and then to adapt this foundation to these dramatically different tasks. We replace its embedding layers and the prediction head while retaining its most computationally expensive attention layers by leveraging the pre-trained weights and also the variable aggregation modules. And then we can, by leveraging this foundation, the fine-tuning becomes significantly faster and also more data efficient. We downscaled the 28 kilometers ERA file reanalysis data to a 7 kilometers resolution by fine-tuning the its 100 media parameter version. And model performance was evaluated against graded observations using both the scientific and the image-based metrics as shown in this table. And it demonstrated that the orbit can produce accurate high-resolution precipitation forecast from the low-resolution inputs, and it can even capture that extreme precipitation values as shown in these figures. And in addition to the weather forecasting and the downscaling, we also fine-tune orbit foundation to accelerate land surface model simulations. So our ORNL team developed a high-resolution kilometer-scale DOE's land surface model. And it's accurate, but it is also computationally expensive and mainly due to the biogeochemical spin-up process. And then to address this challenge, we aim to build a fast emulator of ELM to spin up its simulation with the initial focus on the computational bottleneck, that's accelerating the BCC spin-up process. And this is a difficult problem as we have the multimodal data as inputs, as you can see, but we only have a very limited number of training samples from the expensive ELM simulations. But the results is very good despite the challenges. So, and the results indicates that the machine learning outputs closely match the ELM simulations across about 400 variables, and its resulted initial conditions lead to the equilibrium with the NEE approaching zero almost globally. And right now, the relatively large errors occur in the tropical regions, and we analyze it is likely because there's some missing process or variables not yet included in the machine learning models. And then this limitation also highlights the opportunities. So moving forward, we will incorporate more processes and variables in the training, hopefully can improve the prediction accuracy globally. So the development of orbit has earned the recognition as the Golden Bell Prize for the Climate Modeling finalist, and also won the Top Supercomputing Achievement Award, highlighting its impact in advancing the AI-driven Earth system modeling. And this work is still ongoing, and beyond the applications in the weather forecasting and the downscaling, and also the physics-based land surface model acceleration, we are also exploring the other applications by leveraging this foundation. In addition to developing the orbit for the Earth system modeling, we are also building a foundation model for the natural hazard assessment and response. So as we know, the natural hazards such as floods, landslides, and wildfires are becoming more frequent and intense, and increasing the demand for the advanced predictive models that can enhance the disaster preparedness and the response. And then to address this challenge, we are developing an AI foundation model that integrates the multimodal data from different remote sensing and in situ measurements, and also build the infrastructure dataset, and to improve the flood prediction, land cover monitoring, and the global mapping of the built environment. So this work is still ongoing. So, but we do see some good results, especially in the stream flow predictions and compared to our previous baselines. And we are actively developing this foundation model, and hopefully it can leverage different remote sensing data to inform the natural hazard assessment and response. And for the energy and water management sectors, we are developing a probabilistic seasonal hydropower forecasting models to enhance the long-term planning and the resource allocation. And this model integrates the meteorological, climate, satellite, geospatial, and also in situ data with advanced machine learning techniques to predict the monthly hydropower generation up to 1 year in advance. And this forecast can be generated for both the individual hydropower plants and also aggregated energy regions across the United States by leveraging the graph neural networks to learn the similarities and difference between these hydropower plants. Hopefully, it can provide valuable insights for the grid management and the reliability. And this is also an ongoing project. Okay. In addition to the fundamental research and method development, so our team also supports a broader research community through the open source software tools. So here listed the 2 examples. The first package leverages the conditional generative AI to quantify the parameter uncertainty and generate the probabilistic forecast. And the second focuses on the quantifying the uncertainty in the machine learning model predictions and helping the improve the trustworthiness and the reliability in the AI-driven modeling. And both tools are freely available as shown in this GitHub. So please check it out if you are interested. Okay, this is my final slide, and it's about the time. And this slide summarizes our research on advancing land surface modeling across these 3 paradigms: the physics-based model, data-driven machine learning model, and the big data-powered AI foundation model. So I've touched each topic briefly, and I hope it gave you a sense of the directions we are exploring. And I'm sure you will have a lot of questions, and now is the perfect time to dive into it. Thank you.
Thank you very much, Dan, for this extensive and comprehensive overview of your work on the uncertainties for machine learning and the different type of machine learning and quantification of the uncertainties. So if there are any question on the Q&A, please put them there. But I would have a first question maybe from your experience in the quantification of uncertainties and with the machine learning. So given the different nature of distribution and the risk for overfitting for extremes such the flood or longer timescale drought, I mean, how much gain do you think we could get in terms of uncertainty reduction when combining, for instance, the LSTM with the basic physics, like as hybrid models?
Yeah, good question. So in terms of extreme events, it's really hard to predict, especially if this extreme event haven't happened before in the historical data. So it's really hard to predict it. As you mentioned, right now we have the 2 approaches. One is first applying just standalone data-driven methods, and then use the uncertainty quantification to see whether it can capture it or miss it. So it's just an indicator, but it cannot fundamentally address the problem. And then eventually we can use the hybrid models, combine the physics and the machine learning. For example, if for some physics we have a good understanding, we can leverage the physics-based models. For some parameterization, we don't have a good understanding, but if we have a large number of data, so we can build a data-driven machine learning models and nicely combine them together. And hopefully it can help us capture the future trends by leveraging the physics, and also can leverage the data-driven machine learning models to capture some small scales processes.
Okay, thank you. You have one question in the Q&A?
Yes, so it says, what do you find to be the most important component of the foundation model to be generalizable? So, right, so a good question. Right now, we developed a foundation model, and I also showed the 3 fine-tuning cases: the weather forecasting, the weather downscaling, and also the physics-based land surface model acceleration. So the weather forecasting, we got a solid results in comparison with the state-of-art methods. And the downscaling is still going on, but as you can see, the preliminary results is very good. And it's right now limited to the weather downscaling data. And we are right now working on to the climate projection data. And hopefully it can downscale the 1 degree climate data to our several kilometers for our regional use. And then for the, I would say building an emulator of the land surface model, especially to accelerate the biogeochemical spin-up process, is the most challenging one. So, but it is a important problem. We know the BGC spin-up is very computationally expensive, but if we can solve this problem by leveraging the faster to evaluate emulator, we can save a lot of computational cost and enable to run the large ensembles to capture the different scenarios. Right, good question, thank you. Hi, Elias. So right. So the question is, I assume the emulator you showed was for the ELM v3. As ELM continues to be developed and the model evolves, would you have to retrain that emulator to mimic the newer version of the model? Is this easy to do, or is retraining rather expensive? Okay, yeah, good question. So not just limited to the ELM, for all the physics-based land surface models are evolving, as you can see that figures, right? And then right now, we hope we can build a good foundation there. So essentially build a good workflow, and whenever you change it, we can leverage the new versions model simulation data to quickly change, and hopefully can still maintain that accuracy. Another question is, so I was wondering if I could get, oh, okay, that's not. More questions?
Okay, so apparently there are no more questions then. I would like to thank you again for this great talk, and yes, to keep the machine learning and the physics hand in hand. And thanks again. See you next time.
Yeah, thank you all. Bye-bye.